unpenetrating radar. First of all, let's talk about GPR. GPR, first point of GPR is it's a shallow subsurface investigation method. It's a shallow subsurface. What do I mean by shallow? That means it will be investigating up to 50 meters. So nowadays there are several options are available, and these options are GPR means ground penetrating radar. It's basically scan the subsurface. In a layman's term, you can say it's scanning the subsurface. So in case of shallow subsurface meter, you have only 50 meter. I mean, there's 150 feet. Only that much of information you can get. So where it can be suitable enough. So for very high resolution, one more point it has, that is a high resolution is a high resolution cost effective. Cost effective means one person can, most of the time one person can do hold the survey. Okay. Other than remember that one thing I have mentioned during seismic, people used to do for petroleum exploration or hydrocarbon exploration. Generally, companies involve this reflection seismic technology, and there they have used generally dynamite or other seismic sources. Okay, that is the costlier enough. Dynamite is not much costlier, but the permission to get the dynamite or to blast the dynamite, that is costlier. So if you are damaging some land, you have to fill it up. Okay. Other than this, around 550 people required to do a survey. To do a 3D survey, around 550 people required, and this cost means it is very costly. Per day, they are expending more than 10 lakh to do the survey. On the other hand, you will be buying a system of GPR, and it will give you the information around up to 6 kilometer. You know that petroleums generally existed up to 5 to 6 kilometer, or at a depth of 5 to 6 kilometer. So it can give you the depth of 6 to 10 kilometer, and the expensive. Then the data processing steps are very complicated. It is very expensive. I'm talking about seismic in the topic of GPR, because seismic and GPRs are like brothers. Seismic is the big brother, GPR is the small little brother. So seismic basically involves the acoustical. GPR basically involves the electromagnetic. Seismic basically go up to 6 to 8 kilometer depth. Same processing style, same processing criteria, or same survey method. Generally, the data acquisition method is generally involved in GPR also, or can be involved in GPR also. Similar pattern is there, but this part is expensive, this is not. Once you bought the GPR system, say 50 lakh, you expend at once, and you will have your GPR system, and you can do the survey. But it will give you a high resolution shallow surface survey, and seismic generally do not occur in the hard rock terrain. So that's why GPR is required to investigation or investigating the water table. See, water don't have any economical it has low economical value. If I say no economical value, that will be wrong. So it has a low economical value than the petroleum or the hydrocarbon. So that's why people don't want to spend much on the water. And water table generally, if it's in the 150 feet, so we can easily identify the water table using GPR. Now, ice sheet thickness in glacier, it could be around 1 kilometer. That can also be done or can be detected by GPR. Then you might ask me, or you might question me, this sir, you told me that it's for the shallow subsurface and you are talking about 1 kilometer range. So it can only be happen in the glacier or ice sheet condition. That why this can image up to 1 kilometer in the glacial condition and up to 50 meter in the shallow subsurface condition, in the sedimentological condition or in the hard rock condition. That will be discussed in the theory part. Okay, so let's talk about. So this is the syllabus. So ground penetrating radar is now a well accepted geophysical technique. It's a very recent technique. You can say it's generally developed. So the concept or idea of the GPR is your EM theory. And as you know from the previous classes, that EM theory is 100 years or more than 100 years old technique. So the concept is there, but after publishing some paper, after some work on the seismic and GPR, people commercially produces GPR around, not commercially, but say that the electronics guy or the electrical and communication engineering guys or some scientists from that field, they were developing some hardware to detect the underwater moisture content or underground subsurface condition. So generally it developed, let's say, in the 1990, but commercially it available from 1995. Generally, so in 1995, I think GSSI, that's the name of the company, Geophysical Survey System Incorporation. Okay, so they first commercially produced or developed a GPR system, and so everything will be discussed here. So ground penetrating radar is a very well accepted geophysical technique. This method generally uses a radio wave probe the ground, which means the low Ross direct emission. So the range of GPS generally used from 10 megahertz for geophysical or the geological exploration to 2.6 gigahertz, and this is for the concrete inspection. So suppose there is a concrete and you suppose there is a bridge kind of structure is there, or some kind of tunneling kind of structure is there, and you want to detect if there are any voids in between the bridges or in the um, in the that concrete like structure. So then you will be using this 2.6 gigahertz. Other than 10 megahertz is okay. You know mega, mega means 10 to the power 6 and giga means 10 to the power 9. Okay. So generally it ranges between 10 millihertz to 10 megahertz to 2.6 gigahertz. Okay. So that will be discussed later. First you understand the uh, for what GPR is very useful. So in its earliest inception, GPR was primarily applied to the natural geological material, and now GPR can be applied to host of other media such as nowadays people are using GPR in many cases. Okay, and they are even doing the integrating part also. Uh, so recently there is a trend of using the integration of several geophysical method in a single as a single tool to observe it. So not only they are believing on one or relying on one system, but they are using two or more geophysical data to do the joint inversion or to the joint modeling to get the idea of the subsurface, which will give you the accurate idea. Okay. So the existence of numerous, and you can easily incorporate GPR with ERT because they depends on the electrical and the magnetic. GPR generally depends on the electrical and magnetic properties of generally the electrical properties of the material, and what are the electrical properties, what are the magnetic properties, that will be discussed in details. The same methodology can be applied to glaciology and the non-destructive testing of concrete structure, and the spatial scale of application varies from the kilometer to centimeter. So the most common form of GPR measurements deploys a transmitter, and as any GEM system, you know that there is a transmitter is there. Transmitter will be transmitting GPR signal, that is the EM wave, that is the pulses. Generally pulses are used, and receiver will be receiving it. There will be a control unit who can control or record the data. Okay. So in some application, trans-elimination of that will be discussed later. Okay. So use of the radio waves to sound the earth was first perceived before 1950, before 1950 or in the 50s. Then after with the demonstration in 1961 or 1960, they are developing a idea that using the EM method, we can, or using the PM method, they have that time they have the idea of electromagnetic theory, but GPR idea that gradual transition of the concept of to sounding soils and rock, which basically begins in 60s, and it has been continued ever since. If I talk about the history, that in 1989 there is a Davis and Annan. This Annan is the Peter Annan. These two were the very famous guy, and he was working um, or working as a electrical engineer, I think, in some company in USA. And this Peter Annan guy, he has developed many methods, many theories, or he has given. Basically, he is the father, you can say, of GPR. Okay. Then Annan was there, Joel is there, H.M. Joel, Harry M. Joel. These are the pioneers of this method. Okay. So then Anand gave a summary of 2002. So Anand gradually developed, and he has written numerous paper on this CPR, which has cited, people has cited. I mean, to if you want to write any paper on GPR, you have to cite Anand. Okay. How big he is. Basically, they Anand basically developed the theory from scratch. And after that, the geological stratigraphy discussed in 2003, Bristow and Joel. It's a very good paper published in Sedimentology. And first successful attempt of hydrogeological study was done by Rubin and Howard, 2005. So see, it's not a very old technique. Okay, and there are other thing like top is there in 1980. They have given an idea of a how the permittivity will change, and from the permittivity, so in a moisture or in a wet soil, what will be the relationship between um, the moisture content theta with permittivity epsilon. So top basically in 1980 they he has given um, one idea about that moisture content and permittivity relation. Why I'm saying this tops paper is a very old paper, but this is still applicable for GPR signal, or from GPR signal or GPR data modeling, from where you want to model the subsurface moisture content. So ground penetrating radar has many similarities with the wave propagation method in the subsurface imaging for well exploration. So what are the propagation method in subsurface imaging? That is seismic. And this analogy basically used to transfer technology from petroleum industry to the geotechnical arena. And there are some paper also in 1995. I forgot the name. Uh, Carcioni, something like that. And following that paper, people can. So, what about the development is happening in the seismic? What about the theory, or what about the modeling technique developing in the seismic? They are modifying it, and they are applying it to the GPR. Okay, so part of my PhD work was also on that. So there was some existing seismic inversion technique. I took it and I have modified it like my own, and I applied it to the I applied it for the GPS system. So ground penetrating radar has established itself a successful technique for a wide range of shallow subsurface evaluation. So what are the ground penetrating radar application? Employs is basically employs the electromagnetic wave to map the boundaries between the different dialectic layer, and it can be applied in several cases like civil engineering, hydrogeophysics, geology, archaeology, neotectonic, military application, and glaciology. Okay. So this work and this civil engineering and utility work I was doing as a part of a consultancy project. My supervisor has got at the currency building. You know, Gori. Do you know the currency building? Anyone know the currency building or the Megan David Synagogue?
No, sir.
So it's in Kolkata. It's a very ancient technique. That was the. It's called the বাংলাতে বলতে টাকসাল টাকসাল building. So it was the Tangsal during the British period. Okay, so I was doing the survey there. Then I did survey in Varanasi, then Paradeep, Meteor Mike, Varanasi. That's a dome from a this structure. If you could see, so it's a dome from around 1500 or 1600 Mughal Empire. Okay, someone's tomb is here. So there are a whole lot of GPR application you can do using GPR applications is there. So that groundwater inspection, bridge deck analysis, generally archaeological investigation. Nowadays, people are raising archaeological investigation. SSF is giving a very high resolution data. So without excavating, you will have the idea of that archaeological excavation part. That will discuss with some case study and groundwater inspection because GPR generally depends on if I GPR is a electromagnetic wave and the layers boundary is getting reflected from the layer boundary and these layers are defined by mu, epsilon and sigma. Mu, epsilon and sigma. So this is mu1, epsilon 1, sigma 1 and this layer has a mu2, epsilon 2, sigma 2. This is a different layer. This is a defined layer and this is a defined layer. Okay, so this is how the layers are defined in any electromagnetic method or any for GPR system. And I was discussing that depending on the dielectric constant contrast, so the difference between the conductivity or difference between the permittivity will give you the contrast, give you the idea of the boundary of this two layer. That will be discussed. Don't worry. So in the geological investigation, you can do sedimentological mapping, hydrogeological investigation, soils, peatland, and biomonitoring. You can do contaminant mapping, LANAPL, DNAPL. I think you know better than me about this. Aeolian dune investigation. You can do glacier and ice study. You can do. So what's the basic principle of GPR? The basic principle of GPR is from electromagnetic theory. Generally, we do not use epsilon. Rather than using epsilon, we took a dimensionless parameter that is your epsilon r, relative permittivity, which is the material permittivity divided by vacuum permittivity in the vacuum. Okay, so this is epsilon r equals to epsilon by epsilon. So we generally take the epsilon r. Sometimes it denoted as kappa k. So I'm defining two layers. First layer, that's the blue layer, and the second layer is the yellow layer, let's say. And it's giving you sigma 1 K1 and sigma 2 kappa 2. Sigma 1 kappa 1, sigma 2 kappa 2. So what happened in transmitter? From transmitter, will be transmitting EM wave and it will be reflecting from the boundary between these two layers and it will be recorded here in the receiver. And there is a processor, means the control unit, which will be controlling all the things. So the parameter you have to set, what duration you want to take. Okay, that thing you have to decide on the spot. What duration you have to take, what other parameters. So you are giving it wave. Okay, So you are transmitting basically wave, and the wave designing and the receiving and recording and storing the name of the file, everything can will be done using a control unit. Okay, and the foundation basically lie in electromagnetic theory, and GPR has been widely used to investigate subsurface structure or buried artifacts because GPR systems are lightweight. It's a lightweight, portable, robust, and you got the idea. It's a digital system where data can be viewed in real time. So how GPR system works? GPR system works by sending a tiny pulse of electromagnetic energy into the material, and it will be recording the strength and the time required for return of any reflected signal. If you remember my if you remember from the previous class that I talked you about the well and throw pebble incidents. So suppose this is a well, and up to this there is a water. Up to this, let's say up to this there is a water. So up to this there is a water. What will happen? You will be doing this experiment. I think you will be throwing a pebble or a big boulder, rock or rock boulder, and you will be throwing here. After throwing it, it will be impacted. So after impaction, what will happen? This impact will create a sound. This impact will obviously create a sound, and this sound will travel all the way. So first it goes like this, then it will be traveling all the way, and it will reach your ear. Suppose there is your ear, and it will reach your ear, um, and from that you can say that the water is at a deeper position or the water is at shallow position. If it taking much time and the amplitude or the thumping sound is very weak, then you can say that okay, it's in a deeper position. And if it's in a it's takes less time and the thumping sound is very strong, then it will be, because it have to travel, it had to travel a very less distance. That's why the attenuation of the signal will be very less. So from that experience, you can say that oh, okay, it's in a shallow condition because the is taking less time, and the thumping sound is louder than the previous case. Similar analogy has been used here. Okay, so suppose there are two layers or two dielectric layers and two dielectric layers, and these dielectric layers from boundary is getting reflected. So whatever you are recording here, you will be recording the amplitude of the signal, and along with it you will be recording the time it's taking. It's called the two-way travel time. One way, two way. So same thing, same portion they are traveling twice. Once is going and another is coming back. So that's why it's called the two-way travel time, TWT. So these two things will give you the idea of the boundary. And one more thing they basically depend on, that is the dielectric contrast. So if it's a water table, suppose this is a water table. So this portion is your saturated condition. This is the unsaturated condition. So water table, water has a very high impact on the GPR signals, because the water has a epsilon r or the kappa around 81. Air has a epsilon r equals to 1. So when it's saturated with water, that means the epsilon r 2 will be greater than epsilon r 1. So epsilon r2 will be greater than the epsilon r1. So there is a contrast here. So this water table will appear as a high amplitude signal. So if you are giving the signal here, so this will a recording signal like this, and this will give you a very high amplitude signal, very high amplitude like this. Okay, because there is a dielectric contrast. So you are keeping white and black, and you are taking a photograph, and you can easily find out the boundary. But if you are taking gray and black and your camera is not so much high resolution, then the boundaries might not be as clear as the previous case. So that's simple fundamental principles generally used here. It records the electromagnetic energy waves reflected from the boundaries of the subsurface materials having different dielectric constants. The strength or amplitude of the reflection is determined by the contrast in the dielectric constant. That's the basic fundamental principle. We are seeing the contrast in the dielectric constant. I mean the permittivity, the relative permittivity, and the conductivity. Generally, permeability, for the sake of simplicity, or generally mu do not change or does not change over the area. So mu will be same, or if it's changing, then it will be very negligible amount. So we generally take mu equals to constant for all the layers. Mu equals to mu zero we generally take. Okay, and we only changing the sigma 1 epsilon 1 sigma 2 epsilon or epsilon r1, that can be written as kappa epsilon kappa 2. So that's kappa is your dielectric constant or relative permittivity, whatever you want to say, you say it. So we are basically scanning the subsurface in a line, if I am to say, by scanning the subsurface, and we are observing the dielectric contrast. And this dielectric contrast can be understanding from the records, that from the records and from the records how you would understand that it's a high dielectric constant or low dielectric constant, because it will give you an idea of by seeing the amplitude and the time it's taking of the receiving signal. So by this you can identify the boundary and other the variation of the dielectric materials. Okay, so that's the basic principle of GPR. Now let's talk about the. I have talked a lot about the permittivity, permeability, and conductivity. Let me recap or refresh your memories about that. Then I will go for the main GPR equipment system, a processing, acquisition, how the acquisitions are done, how these things works. Then we'll go for that. So I want you to write down this whole thing, whatever I'll be discussing. By that, you only able to understand. So I'll send you a book, and from that book you can read it. But before that, you have to write down the main points.
Sir,
So take a note. Yes,
how many credit points are there for this assignment?
20 marks.
20 marks. Okay. Sir, actually, it will take much more time.
How much time?
Writing paper and all.
So I want you to. It's a 15 pages writing. I don't think it will take much time. You are having so much time. So you have to submit it by 30th June and do that. Okay.
Okay.
Now everyone knows about the Faraday's law. Sorry, everyone knows about the Maxwell's equation. So these are the Maxwell's equations. Write this down. I've already discussed. Maxwell's equations are basically a combination of four equations. Some of them are from electrical properties. Some of them are from magnetic properties, and both are combined, giving you the properties of the electromagnetic wave. Okay. So understand the physical meaning of the materials, electrical and magnetic properties, and how it is related to GPS signals and attenuation and the wave propagation velocity, that will be discussed here. So I'll be discuss this theory very briefly. Write down these formulas. That's Faraday's laws of induction is here. So Carl equals to, Carl means I'm taking the 3D 3D body, 3D volumetric body, or 3D consideration. So Kali equals to minus del B del T, then Maxwell's modified circuital law, Kali is equals to del T plus J. There are several methods to prove that. Gauss's theorem electrostatics is there. Gauss's theorem is magnetostatics is there. From that, I've already discussed you that the associative constitutive relationship introduced the relevant material properties parameter of permittivity, magnetic permeability, and conductivity. So these are D equals to D is the diffusive current. D equals to epsilon E, where epsilon is the permittivity of the material, farad per meter. I'm going to that. Okay, so basically the Maxwell's law depends on D, J, and B, or related to G, D, J, and B. So D, B, J, okay, and E. So it can be written as D equals to epsilon E, J equals to sigma E, and B equals to mu H. So B giving you the magnetic field strength, H is also magnetic field. So mu is giving you the permeability value. It's the only magnetic properties. Other than this is the static current properties, and this is the dielectric properties. So from the dielectric theory, you are having this one. From the static current properties, you are having this one. So these two are from the electrical point or electrical theory, and this was from the magnetic theory. So mu is the magnetic property. Remember that. So this is basically, or the simplicity or the simple assumptions are basically due to the uniform homogeneous material. In real case, this sigma, mu, and epsilons and d are these are the complex quantities. Okay. So subsurface materials are often described as dielectrics with their parameters, permittivity, and conductivity loosely termed as their dielectric properties. So strictly speaking, the term dielectric describes a class of non-conducting material that can accommodate a propagating alternating EM field, such as only materials containing bound electric charges. So in physics or in electrical theory, when we refer dielectric, that describes the class of non-conducting materials, but it might have a capacitive property, or it can accommodate a propagating or alternating EM field. That's called the true dielectrics. But here will be I'm using the dielectric terms I say loosely because I'm considering all the materials are dielectric properties. It allowing to propagate the EM field, alternating EM field because it's electric and magnetic field. So it's a sinusoidal wave, and electric and magnetic field directions are changes because they are both perpendicular. I have already discussed about the EM field or EM wave propagation. So if there are free charges available, then under the influence of the applied EM field, these will be flow through the material as the pore fluids of saturated sands, producing the attenuation and loss of energy. In reality, all subsurface materials possess some form of free charges. And I might ask you about the difference between permittivity, permeability in the exam. So be sincere about this topic. Now, in extreme cases, material containing the high degree of free charges is effectively a conductor, where measure of the electromagnetic energy. So, in dielectric constant, let me define you. Let me give you an idea about the conductor and receiver. So, when a conductor happens, how the electric circuit current flows. So, if there is a free charges available, and the amount of free charges available in the material like copper and other. Aluminum or any metal, and what happen here, any metal is conductive of electric current because they have more electrical free charges, and these free charges will travel through this direction and it will propagate it electrical current in this direction. So that will be the electrical current. Now for the dielectric constant, that basically create a dipole kind of thing, plus and minus, then it will be plus and minus, and in presence of any electromagnetic wave, the plus and minus and these things generally change, and it basically allows the electromagnetic wave to propagate. So the current propagating through this, the current associated and from this EM wave, the current propagating this through this will be very less. In general, dielectric properties are dielectric materials generally used or many electrical or electronic circuits. Okay, and here we are considering earth material as it dielectric materials. Okay, which has which property basically depends on mu, permeability, epsilon, and sigma. Now, what is permittivity? After discussing permittivity, then I will discuss about the dielectric constant, that is the relative permittivity. So permittivity describes the ability of material to store and release EM energy in the form of electric charge, and classically relates to the storage ability of capacitor. You might have heard of the capacitor, generally used in your fan. Basically your fan, there is a capacitor, and sometimes you might have heard that fan is not moving faster. Okay, and that's not moving faster and getting slower day by day, because your capacitor is that's the common name of the nickname of that capacitor is condenser. So this condenser is not working, or the capacitor is not working, that's why your fan is not working. So this dielectric system, because you cannot apply a direct current to any electrical appliances, so there are several lots of complicated electrical circuits is there, one among which the dielectric um, um, raw material or dielectric capacitor is there to control it, to control the fluctuation of the current, to control the current flow in that appliance. So these are complicated things, but you understand for your sake, permittivity basically describes the ability of the material to store and release the EM energy in the form of electric charge, and classically it relates to the storage ability of the capacitor. So if the permittivity is higher, then the propagation of EM wave will be more easier. So the material will, or the dielectric material will appear, then if the epsilon is higher, then the dielectric material will be more conductive to electrical current. Okay. Alternatively, it can be described as the ability of restrict the flow of free charges or the degree of polarization exhibited by a material under the influence of any electric field. So it is a generally we use the non-dimensional terms, that is the relative permittivity term, where kappa, relative permittivity means the dielectric constant. So dielectric constant kappa equals to epsilon r equals to epsilon by epsilon naught. So where epsilon is the permittivity of the material and epsilon naught is the permittivity of the free space or vacuum. So relative permittivity for air is 1. Remember that, write this down. And relative permittivity of water is 81. And epsilon naught is 8.8542 into 10 to the minus 12 farad per meter. Coming from Faraday, the great scientist, it called farad. Okay. So in fan, you might have heard that they are using in the microfarad range 25 to 25 to 2.25 microfarad to 2.5 microfarad. Okay. So the permittivity of subsurface material can vary dramatically, especially in the presence of free and bound water. And the permittivity of air water is relative permittivity, or the dielectric constant of water is 81. So if water content is more, the permittivity or the dielectric constant of that material will be more. So if it's wet sand, the permittivity or the dielectric constant of the wet sand will be more comparing to the dry sand, because in the wet sand there is a water, and water has a highest permittivity value, the dielectric constant value, which basically plays an important role for changing or for variation of the dielectric properties in the subsurface. So generally we are mapping the underground layers mostly due to the water or the moisture content. So if the higher the epsilon value is here, that means the less radar penetration. If it's very conducting, then it will be more attenuating. That I will discuss. The conductivity describes the ability of material to pass free electric charge under the influence of any field. So in metals, this charge is related to the free electrons of metal atoms, while in fluid they are represented by charges of dissolved anions and cations. So these charges basically carriers rapidly accelerate to the terminal velocity, generating the conduction current. And this conductivity basically are GPR frequency dependent. At low frequency, the charge response is effectively instantaneous and the conduction current in phase with the electric field. In this case, the conductivity can be represented by a real static value. So generally, conductivity can be represented sigma has two part. One is sigma dc plus I sigma ac. It's a complex term. Okay, so I won't go much deeper on this. I'll suggest you to read it from the book. So high sigma basically, if there is a conductive material like is seawater, if you find seawater on the top, then the GPR won't work. You have to understand the physical meaning of that. So high sigma inhibits radar penetration. So there will be nil penetration or very less penetration. So what we need to do for GPR survey is that we need to find a dry condition, dry soil. It's preferred. So your topsoil should be dry soil. If it's a dry soil at the top, then you have the water table at certain depth. That can be imaged very beautifully or very in very high resolution conditions. So if we say this water table is in between in dry condition, then it can give you a very high dielectric contrast, and this dielectric contrast will appear on the radargram. The radargram means the record we see on the reflected or the reflected signal from the boundary is recorded at the receiver. That's recorded record. This recorded signal is called radargram. This whole 2D section is called radargram. Remember that. And for if it's a seismic system, then it will be called as a seismogram. But it's a GPR system, that's why called it's called as a radargram. Now for the dry condition, it will work fine. If the overburden is dry, then it will work fine, and if the overburden is coarse, then it can work fine. But if the overburden is clay material, it's a fine grain material, then GPR signal will be attenuated more in that fine grain material of clay. And because clay has a conductivity of around 100, and that's a huge conductivity situation, and sand has a conductivity in the order of 1 ohm, 1 Siemens per meter. Okay, so sand is far resistive than the clay material. So if it's a conductive material, what happened? If it's a conductive material, consider two layers. This layer is the conductive material. This layer is consisted of the conductive material. So what will happen? The EM signal will fall if it's passing through, when it's passing through this material, it will be dispersed in several directions. It can go. Okay. Suppose there are several ways to go. Suppose you are there is a fracture zone in a rock. I'm giving you an analogical idea, and this fracture zone has high permeability. What will happen if you pour water? It can go several ways in that layer. Okay, from here. But if it has only one fracture zone which can pass through the second layer, then it will go only through this. Same things happen here. So this is the conductive thing. So it can disperse in any direction, and the signal will eventually lost. But I'm not interested in the overburden. I'm interested in the layer boundaries or the layer boundaries below that. So you have to reach here that this thing should be resistive, the overburden. Okay. If it's a resistive, then it won't disperse in like this. So it will follow one path, and it will be following like this, and it will be reflected like this. So one portion will be reflected like this, and another portion will be reflected like this. Then it will be reflected like this. So this is how GPR works, how the conductive overburden is not acceptable here. So whenever you will be going for a survey or GPR survey, you have to look for a dry condition. You have to look for, you have to avoid the wet condition of the soil, and you have to observe for if it's a um, if it's a fine sand condition or the clay sand condition or the clay material at the top, then you won't get any signal, or you will get much attenuated signal. The depth of penetration, suppose it can go up to 10 meter, but you will be getting around 2 meter in the clay condition, or you might not getting any signal back from the targets. You will be having some noises we used to see when we used to see in the TV, where when no signal is there, then how this works generally. Okay, there is a monotonous frequencies, or that thing you can see. So that's the basic fundamental idea to do the survey. So highly conductive soils are not ideal for GPL investigation as soils with a low sigma, such as dry sand. I've already discussed about that. Now let's talk about the permeability. Generally, we didn't care for the permeability. Permeability, in most of the cases, we consider the mu equals to mu zero, and permeability also give you the idea or the ability. It's the magnetic properties. uh, it's a ability, or the it has a little effect on the propagating GPR wave. So that's why we don't consider about the permeability part. So high permeability basically inhibits radar penetration, and most soils have the relatively low permeability, and we don't care about the permeability. And for your sake of understanding, that is the Dale operator, gradient operator, because this will be required in the next slide. So try to write this down. Do you know what is I hat, what is J hat, what is K hat? Gori, what do you mean by I hat? What do you mean by J hat? What do you mean by K hat?
So these are vector terms.
These are the direction vector along x-axis, along y-axis,
Yes,
along z-axis.
yes,
I
sir.
means the along x-axis, y-axis. These are the directional vector, and get square is can be written like this. Now, what are the relative permittivity? Means the dielectric constant and the static conductivity value. Static conductivity means the DC conductivity we are considering. So generally for clay dry, it has a conductivity of 100 millisiemens per meter. There was a question in your medicine, I think you remember. So relative permittivity epsilon average is around 2 to 20. Generally the relative permittivity around 15. Fresh water has a conductivity 0.1 to 10 in order, and it has a relative permittivity of 78 or 80 81. Generally we take 81. Sea water has a conductivity around or in the order of 1000, like 4000. How conductive sea water is? So it can be understood that 81 to 88, and I have delineated freshwater and seawater boundary, depending. So you see the contrast here. So if there is a freshwater zone at the top and seawater zone at just below it, then you can easily find out the boundary, because the conductivity difference you see. Permittivity or the constant is dielectric constant is almost same, but the contrast you can see from the conductivity, and when there is a contrast, GPR can work fine. And generally for soil, like it's a coastal soil, we generally take the relative permittivity around 10, and the coastal dry soil, the conductivity around 0.01 to 1. So these are very resistive thing. Okay, same goes with sand and sand weight. So by seeing, so if there is a, suppose if there is a dry sand that has a static conductivity T condition, and there is a wet sand saturated with fresh water, see the conductivity. So let's say the dry sand has a conductivity 1 millisiemens per meter, and wet sand has a 10 millisiemens per meter. So there is a contrast between dry and wet. what means that there is a water table is there. There is the boundary can be defined as a water table. So your aquifer is made up of sand. I'm considering only sand, and below one is wet and upper one is dry. So there is a contrast, 10 times contrast. So that will appear as a, I'll show you in the next class that how generally water table appears on a radiogram. It basically appears as a high amplitude reflections. And from by seeing so, you can easily identify the water table. So few things are there, few things you have to understand. So ground penetrating radar is most useful in low electrical loss materials. When the electrical loss is low, or what where electrical loss is low, where sigma is low. So sigma equals to 0 or the epsilon is low, or when sigma equals to 0, GPR would see very broad use since the signal would penetrate to the great depth. I gave you the reason. So in practice, low electrical loss conditions are not prevalent. And the clay rich environment or areas of saline groundwater can create conditions where GPS signal penetration is very limited. Water and ice represents the few cases where the single component is primarily present. A simple beach sand is mixture of soil and grains. And one more thing GPR can use. So GPR also follows the intrinsic permeability, permittivity, and conductivity. These are the intrinsic properties of any material. So this subsurface material might not be in a pure condition, like there might be some mixing. So 60 to 70. So suppose in a sand, it's a clay sand, and in that sense, suppose 40% of clay is there. So that proportion, in that proportion, the GPS signal will be attenuated. Okay. So 30 to 40% of GPS signal will be attenuated in that layer. For a simple understanding. So that things is written here. So mixture of materials seldom exhibit properties directly in the proportion of the volume fraction of the constituent components. In many respects, this complexity can make quantitative analysis of GPR data impossible without ancillary information. Now, in 10 to 1000 megahertz frequency range, people had done some experiments and they have found 10 to 1000 megahertz frequency range that the presence or absence of water in the material dominance behavior. One thing I didn't mention here. The thing I didn't mention here is that if the frequency is less, okay, then the depth of penetration (DOP) will be greater. As the frequency is higher, the depth of is less, depth will be great. If frequency is high, then depth will be less. Okay. So high frequency antenna will give you less depth of penetration, but high resolution picture. And if it's and for the low frequency antenna, it will always give you the low resolution picture, and it can penetrate up to great depth. But in the water table, there is a high contrast between the upper and lower unsaturated and saturated layer, and it can easily be understandable because if I am only my sole objective to find the groundwater table, then I might go for the low resolution cases where I can map up to 150 feet. Okay. So in my site, in my area, generally at 70 feet, you will have your aquifer condition. So 150 feet is enough, or GPS system will be enough to delineate the water table. That will be discussed with some case studies, and then you can understand it. A few things you have to remember that bulk minerals and aggregates and mixtures generally are good dielectric insulators. They typically have permittivity in the range of 3 to 8 and are usually insulating with virtually zero conductivity. Soils, rocks, and construction material have empty space between the grains and which is available to be filled with air, water, or other materials. So, if there is another thing, or another application of GPR is your leaking of sewage water or leaking of mm, mm, the water pipe leaking from the water pipe. So this is the water pipe made up of PVC or plastic, and from here the water is leaking like this. And it will, if I take a cross section from the top like a drone shot I am taking, and here you can see this is how the water leakage is spreading. Okay, and this leakage spreading can also be monitoring by GPR, because surrounding these soils are in dry condition, or it has a low dialectic constant than the water. So water has 81, very high. So this contrast or this boundary can easily be identified using GPS study. So water pipe, electrical pipe, if there is anything underground in any area, some of the portions like Fugro Geosciences, there is a scientist, there is a company called Fugro. Some of my friends are working there. They basically survey for utilities. Like in a area there is underground electricity or electrical pipe or underground water pipe, and you don't know, you don't have actual exact map. Then what you will do, you will do a GPS survey, and from that you can identify which one is electrical, which one is water pipe. That will be discussed, I think, in the next class. So first you understand the bulk minerals and the aggregates in the mixtures generally are good dielectric insulator, and they typically have a permittivity in the range of 3 to 8. Soils, rocks, and construction material have empty spaces between the grains, and it can be filled with air, water, or material. If it's filled with air or water or material or any other material, then that dielectric constant will be there, and from that you can identify the void. So it's widely used for void identification, widely used for utility investigation. Water, I have already discussed about the water. Now, water is in the pore space normally contains ions, and the water electrical conductivity associated in ion mobility is often dominant factor in the determining bulk materials electrical conductivity, which resulting soil and rock conductivities are typically in the range of 1 to 1000 millisiemens per meter. Since the pore space of natural materials, except in such unique situations where the vacuum dyeing or some other mechanism assures to, so I will suggest you to read it from there. So empirical derived, as I was discussing, there is a paper on top, the guy named top, this paper. So they basically gave you an idea of the empirical relationship with the moisture content and the permittivity, and from then they have used this one. So this is the top formula. This is the moisture consumed and this is the permittivity. By following the formula, you can determine empirically the mineral soils having various textures and the commonly used relationship between the apparent permittivity and the volumetric soil water content or the moisture content, meter cube per meter cube. So this thing you were can be done using this formula. And there are Archie's law is there, several laws is there. Archie's law will be discussed in your borehole classes. Now, you know the Maxwell's equation, Kali in the frequency domain. Kali equals to this one, Kali is equals to this one, Kali, del dot D equals to Q R omega, del dot B equals to 0. Write this down. In 2D consideration, in 3D sometimes modeling in 3D is much more complicated or difficult. That's why we consider 2D approximation. So when you are doing a 3D thing into a 2D, it has two components. One is transverse electric and another is transverse magnetic. Why transverse electric? Because transverse electric method has electric field transverse to the propagation direction. A magnetic field, obviously the magnetic field will be transverse to the propagation direction. So generally transverse electric mode, we consider ui this direction, and we consider hz and hx. So it's considering of, it has two component, ui, hz and hx, and the wave is propagating along this direction. Similarly, this is the T mode. Similarly, for TM mode, it will be the HX. That's the propagating, or HY. So by seeing these two equations, it can be written as get square EY. That's the wave equation you can see this wave equation is gas square Ey mu 0 omega square epsilon Ey. Epsilon is the effective permittivity. For sake of simplicity, you can consider is a permittivity also epsilon minus I mu 0, because I'm not considering, I'm not taking any mu, omega j sy x z omega. So that's the governing equation of the mode, and this is the governing equation of GPR signal in frequency domain. Okay. Now, what will happen in the time domain? In the Maxwell's equation time domain, I have already discussed that Kali equals to LB del T. So it's related with omega, that is the frequency domain. Omega means the angular frequency. It's related with time T, and that will be your time domain equation. So Kali equals to minus del B del T. Kali is equals to del T plus J, and it can be written as del 2 U square U. U could be your E or H. So it could be UI or it could be HY. Okay. So I'm generally denoting in H as a U. So get square U, H or E as a U. So get square U R of T equals to minus mu epsilon del 2 U del T2 minus sigma mu del U del T equals to 0. Okay. So this term is giving you the propagation. This term is due to the propagation part, and this is the common propagation of propagation equation. And this extra term is coming from the diffusive properties of the electromagnetic method. So for the frequency domain method, and this extra term is not here. You can see here. Okay, only the propagation term is here. And this propagation term, the mu zero square, mu zero omega square epsilon is your k square. That's the propagation constant, capital K square. Capital K is your propagation constant. Write this down. And so here you can easily find out the propagation constant time of propagation, and this diffusion part is extra in your time domain. So whenever you are doing the time domain calculation is far more complicated than the frequency domain um, calculation. And the velocity here, as you can see, these are basically dependent on mu, sigma, and epsilon, the propagation equation. You can write the velocity v equals to 1 by root over mu epsilon. Write this down. And alpha is half sigma root over of mu by epsilon. So here from here you can see if epsilon is higher, the attenuation will be. Now, if you are keeping this mu and epsilon constant, then if sigma is higher, then attenuation will be more. So, as a seawater comparing to the fresh water, the attenuation in the seawater will be more. Attenuation of the GPR signal in seawater will be more, because all the signals, almost all the signal, will be absorbed by the seawater. Whatever you are using from GPR transmitter. From fresh water, there is a chance of getting back or getting the receiver signal. Okay. Skin depth is delta equals to 1 by alpha. So sinusoidal signal are characterized by both omega angular frequency and the spatial wavelength lambda, which can be written as lambda equals to twice by v by omega, or omega equals to twice by f. You know these formulas. So in generally, about the distance, if this is a distance, it will be attenuating. This is the amplitude of any GPR signal it's giving you. Okay, this is attenuating like this, and it will be in a exponential manner in generally. So in low loss environment, EM propagate at a finite velocity, and it decay in amplitude with minimal pulse shape change. So at low frequency, the wave properties depend on root omega, which is indicative of the diffusive field behavior, like this. This is the transition frequency where the diffusive dispersive properties to propagative non-dispersive properties on the EM wave converge. So at the low frequency, you see the velocity increases with the frequency, but here the velocity is almost constant at the high frequency condition. Okay. Similarly, the attenuation properties are also described here. So this is the for the attenuation is the low frequency. The attenuation will be root over of omega mu sigma by 2, and that will be the attenuation for high frequency condition. Okay, that's written here. And the transition frequency is in between the low and high frequency, which can be defined as sigma by twice pi epsilon. Now, in GPR signal propagation, you know V equals to 1 by mu epsilon, which can be written as C by root K, where kappa is your epsilon. This can easily be done. So V equals to 1 by root over mu epsilon, which can be written as 1 by mu epsilon by epsilon naught. Okay, and that epsilon naught you can write here. So you can write 1 by mu kappa, and there is a root over epsilon is here. So if you are using kappa S, then you will be using C. So it's basically V is velocity depending on C by root K. V is basically depending on C by root K, kappa. Okay. So it has a direct relationship with the dielectric contrast. If the dielectric contrast is more, the velocity will be less. Okay, because it will be dispersive. The alpha, then similarly the alpha can be written like this, or Z is the impedance. Okay, Z equals to root over of mu epsilon, and Z0 is the impedance of the space which has a value of 377. If you put the value of mu 0, if you put the value of epsilon naught, then you will get the value 377. Write this down. Okay. Now the GPR to primary factor cause the increase of the GPR relative signal that I will be reading from the book. I'm not explaining it. So typically value of velocity are ranges between 0.07 minute 0.07 to 0.15 meter per nanosecond. Typical values of alpha are within the range or with high loss of 10 to 100 dB per meter, and low loss means 0.01 to 0.12 dB per meter. Typical impedance values are 100 to 150 meter. Impedance means resistance in a word. Impedance basically is a complex term. So complex propagation constant gamma equals to alpha plus j beta. This one attenuation coefficient. So in general, whatever we were discussing, d equals to epsilon e and d equals to sigma j equals to sigma e. That's for the homogeneous isotopic medium. But generally, our subsurface is very complex material, and it basically giving you the complex identities or uh, mm, complex numbers of permeability, permittivity, because it have a real component as well as a imaginary component. So following that ideology or idea, there are the velocity can be modified like this. See, and the complex permeability can be written like this. This is how the complex permeability or effective conductivity is written. So I'll share this slide with you. So in your next class, I will discuss about the system design. So this is the control limit. This is the control limit of 200 megahertz antenna. Sorry, this is the antenna of 200 megahertz. Antenna means this is here transmitter coil is here and receiver coil is here. There is a theoretical, there is a zero spacing in between transmitter and receiver coil. This is called the monostatic antenna, and this is the control unit that will be discussed in your later class. Okay, so that's it for today. If you got any question, just let me know. Did you get it, Sagota and Gauri? Have you got it?
Yes, sir.
Yes, sir.
So what about the assignment? Could you do it?